Hey, here we are. It's John Willis and Mark Burgess again. This is actually episode 7, but I think it's the 8th one because we did a part 2 on the last one. In search of certainty. And I think we should certainly kind of apologize for that last one being an hour and a half. Hey, Mark, how's it going?
Good. This is the Halloween edition,
Oh,
so
that's right.
anything could happen.
Well, and then as I was telling Mark, I was late for this. I voted this morning, so all craziness abounds here in the U.S.
Speaking of queuing theory,
That's oh my goodness, 2.5 wait line in the pre-voting lines. Alrighty then. In search of certainty. So we've been playing with a lot of ideas, and again, if people want to suggest ideas, that would be very helpful. We're just going to kind of randomly pick stuff. I do think that working through the In Search of Certainty book. I've said this many times. I think it's a masterpiece. And I think we've done some of that. I want to kind of keep going back. I've got to the problem is it's hard work because I got to go back and read a couple more chapters that I haven't read in about a year and a half, and to be even have
me
a good
too, actually.
yeah, you too, right? Yeah, that's right. Last time there was some things you're like, did I say that? But I want to continue on the book because I think it's a great foundation. But we talked bit. And then near the end, I'd definitely like you to go kind of where where you've gone from there. But it was good. I mean, I think your articles, as I went back and read it the first time, but this time I kind of enjoyed it a little bit more this time. I don't know why. Maybe the first time I didn't catch little subtleties of but the
We're
whole.
in the throes of startup hell, I think.
Yeah,
negotiating.
probably. Yeah, no, you're like, wow, no, what's this? What are we doing? Yeah. So no, but this time it was kind of enjoyable to, kind of how you described how we would get into it here in a minute, but like I think the interesting thing is that it's a classic in search of certainty discussion, right?
Yeah.
Right. It's again kind of people trying to make things, trying to put a box or abstraction around a complex problem without really doing figuring out the hard stuff. So okay, so I figured I'd just go start off a little bit about that, and then I'll give kind of my overview of. And we can interject and play, but like the little bit of what I learned about SDN and how a lot of people got to a certain place, and then a little bit of kind of Brent's been anti-SDN. So Brent was my mentor in and out of the SDN Kool-Aid.
Yep.
So I'm gonna do that, and then I think we can get into the some of the stuff that you say, then we get into kind of distributed versus centralized, and then I just some of your quotes were really cool too. And then I did want to talk about, I had a funny story with this Jennifer Rexford where I naively asked her how come they don't just use Chef or Puppet, and then she kind of whiplashed me with the complexities of edge cases of data plane, and then then we can get into kind of your stuff, and then you're kind of, I'd like you to kind of go over your kind of hack, what we've done, how we've kind of done, what we did. I think this could be educational because a lot of people maybe have listened to this that might not really understand the network complexities, the kind of little overview of the hack and all that. All right, let's give it a rip. Fun times. I'll start the broadcast here.
Headphones, by the way.
Hey, here we are. It's John Willis and Mark Burgess again. This is actually episode 7, but I think it's the 8th one because we did a part 2 on the last one. In search of certainty. And I think we should certainly kind of apologize for that last one being an hour and a half. Hey, Mark, how's it going?
Good. This is the Halloween edition, so
that's right.
Anything could happen.
Well, and then as I was telling Mark, I was late for this. I voted this morning, so craziness abounds here in the U.S.
Speaking of queuing theory.
Oh my goodness, 2.5 wait line in the pre-voting lines. All righty then. In search of certainty. So, we've been playing with a lot of ideas, and again, if people want to suggest ideas, that would be very helpful. We're just going to kind of randomly pick stuff. I do think that working through the In Search of Certainty book, I've said this many times, I think it's a masterpiece. And I think we've done some of that. I want to kind of keep going back. I've got to the problem is it's hard work because I got to go back and read a couple more chapters that I haven't read in about a year and a half, and to have a good. Yeah, you too, right? Yeah, that's right. Last time there was some things you're like, did I say that? But I want to continue on the book because I think it's a great foundation. But we thought today, so most people probably know I had this little startup socket plane almost 2 years ago. We sold it to Docker, but we had Mark come in and do some interesting work with us. And in fact, for the record, I was going to try to recruit him as our CTO, but we wound up getting sold too early. But Mark had, it was interesting when Mark met some of our kind of my network guys, which were deep in SDN. He wrote this really cool blog article on his blog. And let me get the title of it real quick. And it's SDN, basically it's just SDN, software-defined network, or small distributed namespaces. So I thought we'd kind of look at SDN, just a little bit, quick overview, my experience, Mark's experience, dissect the blog, and then, and Mark is really, as always, kind of sees the future very well. And, we'll talk about how network could work, and particularly with containers and all that. Sound like fun, Mark?
Sounds perfect. Yep.
Cool. Well, I think that, so the first thing I wanted to kind of just throw at you anyway, before I get into kind of my little riff on what SDN is, why it worked, why it didn't work, which was, would you agree? I think SDN is a great case study for, in some sense, hubris, or the question that we try to kind of fight or battle or discuss or theorize in this podcast, which is certainty. Like,
Yeah, absolutely. I mean, networking was one of the first areas of computing where we confronted uncertainty on a big scale, because the distances and the distributed nature of it obviously brings up many of those issues much faster than they occur in the space of a single computer or a single server. So that was certainly the case, and many of the networking protocols that were built up around TCP/IP, particularly TCP/IP, were built on principles that are, encapsulated within promise theory, but they preceded it. The networking guys foresaw those things and realized that they needed independence and autonomy and self-healing and all of those sort of good things that we talk about in server systems. And actually, when I started at the university, I was teaching networking for a year, I guess, before I got onto the server part in the master's program, and that came up. That need to understand the indeterminism, the networking, and the whole idea of certainty, and the way that protocols deal with that is a real key part of the networking that every Cisco engineer kind of learns. But the server guys knew nothing about that whatsoever. So bringing that culture into the server space was a really important thing, I think.
Well, I mean, I think that's funny because, I've riffed with you, I think, about how, what we classically on the server side typically call computer science is really has been a misnomer, with the small exceptions of recent distributed systems and all. But for the longest time, what people did as systems people in, compute was, I think, less about computer science, as I think we've discussed, but the network has always been deeply rooted in some pure distributed computer science. Guys like Dijkstra and stuff like that, right? I mean, those guys were doing mind-blowing things, I don't know how many years ago, right?
Right, it's where many of the hard problems were where they put their finger on many of those hard problems in the right at the start. And they've come up again because I guess what happened that revolutionized the data center world now, or the networking world now, it's to my Freudian slip that, is that data centers grew to the point where networking actually became the problem, the main problem, and well, it still is the main problem. We haven't really come that far, I would say. But this notion of building huge data centers that were on a scale that was totally unprecedented, and creating networks that could handle that traffic. It's not just about having fast wires, but creating architectures as well, which brings up a whole new range of problems.
Yeah, yeah. No, I agree. Right, the complexity and so I think so. I wanted to go into kind of one of the early things that when I started picking up on SDN, is what is this SDN thing, and I stumbled across this Scott Shenker, who was actually one of the early Nicira founders, but he was a professor at Berkeley, and he has a presentation that he does to Stanford on SDN, which is kind of ironic because theoretically SDN was born at Stanford, and he even jokes about that. We'll get to that in a minute. But the one thing I loved about what he said, which were the reasons why SDN was invented, and he said it was probably about a year after SDN was kind of the stake in the ground, but he said that he makes this argument that the abstractions in networking are hard, the management of networking is hard, and nobody really understands it. Like, you have this amazing opportunity for change when those three things converge at, like, to your point, scale. And so kind of back to the certainty thing, the history, I guess a lot of people were involved in SDN, just like a lot of people involved in cloud, but most people credit in 2008 Martin Casado, who basically got part of his PhD was OpenFlow. and really was, kind of the stake in the ground invention of SDN, if you will. Casado, being a Stanford professor, creates a startup called Nasir, a product called NSX. In 2012, VMware, at the height of the SDN hype, and we might, at the risk of pissing people off, hubris, that company gets bought for $1.2 billion by VMware, with 4 customers, and really one of them only halfway in production. And therein lies this window of this SDN. So I'll do my brief little kind of overview, and then I'd like to hear your thoughts. But the idea of how I was educated on SDN, to a certain extent, had a little bit of experience in that my startup, which is your classic networks were hard. They're hard to manage. They really didn't have a good, Scott Shanker does this thing where, the reason why compute and, really evolved was, you had some clarity on the abstractions, and in network, it was really just, the abstractions were just almost, I won't say impossible, but at the time, people just didn't get the sense that this growth, the scale, and you were just, accepting these distributed systems that you didn't understand. So the idea was, go ahead.
I mean, they grew in a strange organic way, right? I mean, networking was never planned. It just grew organically from local area networks where people coupled a printer to a bunch of computers, and they had a file server in the 80s, to when we started getting workstations in the 90s. And got a little bit more sophisticated. You had your thin Ethernet, all that black wiring hanging like Halloween decorations from the ceiling, draping around like spiders' cobwebs. And it really never got designed more than that. So we ended up having this notion of a central router to connect, or actually a hub. It was just a hub, right? It wasn't even a router back then. And it was only later when we started adding the long distance networking that we got the routers and switches were separate things. And gradually over time, these two worlds of local area networking and wide area networking have merged into one picture in a kind of a shoddy Tim Burton patchwork kind of sewn up dog way.
Yeah, no, and your article does a great job in it. And I definitely want to circle back, because I think you do a really good job of kind of, explaining, again, not with any disrespect to network people, but the hacks that happen. And so rolls in these kind of academia, very smart people. Martin Casado is a brilliant man. So their idea was, okay, like, we've got to get some control on this. You have this classic network structure of a control plane and a data plane. And your data planes are your packet ins, packet outs. Nanospeed, wire speed. Your control planes are really kind of your control plane, really. And this is where we get into kind of a deterministic, like, is this control plane then in your classic kind of switches and routers, basically your control plane were this propagation of a distributed systems, basically routing protocol-ish stuff, BGP, OSPF, whatever. And those things would magically kind of spray out distributed logic of how to forward packets to all the data planes. And again, back to Shanker's problem was, it was kind of black magic. People didn't really understand how it really worked. They weren't very malleable for evolution, and they were, reasonably hard to manage. And so the solution, in short, was to kind of softwareize and pull out the control plane from every box and say, we're going to have this software-based control plane. And then what we're going to do is shove in deterministic kind of programmable, humans can now say, instead of distributed protocols, just kind of doing things kind of in a way a human really can't understand. I'm going to allow you to create this kind of programming interface, which in most cases is OpenFlow, but not always, and kind of shim in specific deterministic logic in the data plane so that maybe you can segment off a network or create firewall rules in the data plane. That, and the world went nuts. Like, oh my God, this is it. This is what we're going to do. We've got it. Our humans, we can program everything. end the story short, what happened was the hype never lived up to, to really the delivery, which happens all the time in our industry. But it was a hard problem, right? The easy things like segmenting a network worked fine. Nicira, NSX, all the different SDN solutions, really not that hard. Even throwing in firewall rules, programmable firewall rules into the data plane, and this control plane separation thing, doable. But that's kind of where it ended. What the promise was we could do load balancing, and I've heard people call CRUD for networking, and the mismatch there was just the edge cases and the complexities were just way too hard. And in a sense, SDN really hasn't worked.
No, I mean, I have to agree. But I mean, I think one of the things I wrote in that blog was that when I first saw the vision for SDN, I kind of did a facepalm thing and said, what were they thinking? The total reversal of everything we understand about scaling and scalability and uncertainty. But actually, it got a lot of weight from Google. Google backed this OpenFlow protocol, and they said that they had made it work inside the super duper futuristic data center where everything is, 20 years ahead of the curve, and they've got infinite capacity and so on. So they were able to brute force a solution in that way. But in a sense, what happened with SDN was that what always happens in IT is that we forgot the basic ideas about architectural design, and we went straight back to a centralized approach, a controller-based approach where somebody would be pushing a button or pulling a lever to make something happen from some central location. And what's kind of ironic is that networking had to get out of that originally from your central file server with a hub and a printer in a single room in order to be able to get around the country to connect together universities originally, and then later business got looped into the internet as well. So this idea that distributed computing could actually sort of had to be decentralized at different levels in order to scale. And by scaling, I mean not only carrying the necessary capacity, but also scaling the semantics of it, the management of it, the intent of it. Who determines what the network is supposed to do when it's spread all over the world. That problem was solved through a number of technologies, like originally, small localized things like RIP and OSPF, and then later with larger wide area networking protocols like BGP, MPLS, and so on. And that knowledge kind of got thrown by the wayside in order to solve a problem, which is, again, a problem that you would solve in a local area network, which is the SDN problem. Because the SDN was never really cut out to be a distributed computing problem. It was a bigger local area network, like in a data center or something, but it was still local. And the idea that you could suddenly throw a totally different data center into the mix and manage that from the same single point just wasn't realistic because of the latencies. So, I mean, we have the uncertainties of networking are multidimensional, even more so than the server computing, because you've got your latencies, you've got your network speeds, you've got your data errors cropping up that need to be corrected and have retries on packets being sent and so on. Packets may be dropped. You've got certainly queuing instabilities, and then now distributed queuing instabilities, and so on and so on, and it just mounts up. So when real density of networking became a necessity, i.e. first with e-commerce, the explosion of the web, and then the cloud, basically related to the web, Amazon Web Services. All of this sort of contributed to the need to understand networking as being something more than just having a hub in a room, connecting a bunch of things directly together, talking to each other. There had to be some scaling of traffic and some traffic flow management and so on and so on.
What's funny is, as you were saying, the Google thing, you're right. I mean, Google is famous for supposedly running OpenFlow for 10 years, doing very sophisticated traffic engineering, traffic. But it reminded me of the conversation we had in an earlier podcast. Is that it's funny where in a lot of ways, and we're going to probably, if we have any Google listeners, we're probably going to lose them all. But like they now what I think about it is back to something you said in an early podcast, even with the way they do their systems, like they allow their kind of users, to appear deterministically in control, and then could create kind of non-deterministic backend systems, right? And
try to absorb that complexity.
Yeah, and in a sense that it's I saw there was we did a DevOps networking summit, and we had one of the chief network engineers from Google and Brent, who was one of my partners, SoccerPlane, asked him about they were using Yang, the kind of NetConf modeling stuff, and Brent was like, "Wow, that just seems." But it probably the point I'm trying to make is probably even their implementation of OpenFlow is very similar to if you can create a deterministic scaffolding around this subset of complexity, like you can kind of do it well, right? Unlike the average bank or insurance company trying to pick a product that does the same thing, where the horizontal issues that are going to come up, in other words, because again, I was just thinking out loud, well, how come Google got away with it? And in a sense, they probably really didn't.
Well, I mean, they, like with everything else, they were able to exert such brute force with modern infrastructure and super capable people. They had all the smart people, they had all the best infrastructure. So they were able to make it work by brute force. But I think what's dangerous about that story is that there was then this implication that therefore it should work for everybody else who doesn't have that brute force and who doesn't have that expertise. So, I mean, for the benefit of the listeners, we went from this time, the reason for SDN was that all of these routers and switches were basically independent standalone boxes, and you had to go and walk up to them and plug in a serial cable and type in commands to reconfigure ports. It was that primitive. And if you wanted to reconfigure something or reorganize something between organizations, you had to telegram them or send a postal bicycle messenger or something. So the idea that you could actually do it by remote control in software was huge. And originally, of course, we had SNMP, which could do some small things, and then NetConf came along, which could do other things. But they were all fundamentally remote control protocols, which were very fragile, and you had to do them manually on a step-by-step basis. There was no orchestration, to use that term, in the modern sense. So the idea of SDN was to try to create this orchestration layer. And it's in a way, they did it in exactly the same way that people are trying to do orchestration in server containers and VMs now today, with the central controller managing stuff in a local area network. But the crunch is that networks are not local area things, right? They are distributed, complicated things. And it was when the data centers started to have massive scale, and there was this shift in the architecture of software, which meant that because of all these small services talking to one another, traffic in data centers became up to 70% east-west, meaning inside the data center rather than north-south, meaning going in and out of the data center. And that was a huge shift, because previously the network had been designed for this north-south delivery, and it wasn't designed for highly dense traffic flows within a local area system. And so the networking, there are many approaches to trying to solve this. The way I got into this was working with Cumulus Networks, my good friend Dinesh Dutt at Cumulus, looking at how to use...
There's an awesome dude as well too. So anyway.
Yeah, super nice guy, and we clicked very well on networking in general. But so I was trying to use CF Engine to manage routers and switches that they created, because they're just Linux boxes, the Cumulus ones, right? And this idea that you could do distributed coordinated management, in the classic configuration management way, if you just turn up the speed a little bit. And we put together models around this. Actually, in the end, it was never never used by the company, the CF Engine company, but still in my CF Engine branch. But that was a model, it worked. But then along came centralized approaches again, like Ansible and Salt, and people went back to the centralized remote control models. So not only, I think, is networking come up with a bunch of technologies which have gone back and forth, sliding up and down the evolutionary ladder, but also the way people have chosen, the choices they've made about managing the network have slid up and down the evolutionary ladder, from being scalable to non-scalable, from being robust to fragile, and so on. And so it's really, it's almost a comedy of errors.
It is. Again, my kind of mentor of the whole network space is Brent Salisbury, who was one of my co-founders of SocketPlane, and he's the one that kind of started me drinking the SDN Kool-Aid. All the reasons, the Scott Schenker, the programmability of the data plane, the kind of managing, and then as containers kind of bust into the scene, and our startup was around, like, how do we solve a networking problem with containers versus what people were doing OpenStack and just virtual compute. We started realizing the problem was a lot harder, and that's actually why we brought Mark in at that point, because we knew there had to be a distributed thing. And I want to get into the article here in a minute, the blog article you wrote, but just one of the things that Brent came, like one day I'm talking to Brent and he's pretty much, yeah, that SDN stuff doesn't work. I'm like, what? I'm going to, over the phone, I'm going to reach my hand in and choke you, and he just explained that in the end, him being a classic network sysadmin and architect. He worked in a University of Kentucky hospital for like 10 years. He ran OpenFlow for 2 or 3 years before anybody even heard of it on a government grant. But he'd gone through the whole life cycle. And in the end, he was like, his joke is, all those cat pictures we get on the internet, it's from BGP, and that works pretty good. And just to end it, like, one of his latest projects at Docker is he's written an IPVLAN plugin for Docker in our kind of network space. And like, the good or bad, the trombone of network you described, the large scale network providers that are moving to Docker, like, they flip. They're like, this is exactly what I wanted. I just want to have a container. Its egress is out on the physical host, and the stuff that I've been doing for 15 and 20 years will take care of the rest.
Right. Yeah. Brent, another super nice guy and very smart. We had a lot of great discussions, and we agreed pretty much on a lot of stuff when I joined you guys at SocketPlane, right? But a lot of my understanding for this came out of my discussions with Dinesh, where we really kind of, through his guidance, working in this space working in the data center space with the Cumulus knowledge and so on, really came to this conclusion that people are very focused on layer 2 networking for some reason, but layer 3 networking is the only way to go to scale networking at all.
Amen,
for
brother.
some reason,
yeah, sure.
when they decided to implement SDN and implement networking in virtual machines and in Docker and all these other things, they went for this kind of L2 bridge model networking, like they were wiring up some old-fashioned thin Ethernet cobweb, back in the 1990s. And to me, it was extraordinary. But I guess you have to realize that there's a huge cultural difference between networking guys and software guys. And the software guys, bless them, tried to do their best to get to understand networking and fix some of the problems, but they just didn't know their stuff. And so they created this, kind of ugly attempt to extend the notion of locality through tunneling, trying to create VLANs or broadcast domains in the way that you would manage a single local switch. But unfortunately, instead of being like a separation of concerns, it became like a conflation of dependencies. And you had basically the chassis of a Tesla on the body of a horse, and you're trying to ask it to jump hurdles.
Mm-hmm.
tunneling layer 2 through layer 3 and back to layer 2 and mapping ARP tables in real time, and it was just crazy nuts. I mean, if anyone looked at that design, they were
Yeah, it's like if you came in from a planet and said, "Whoa, whoa, whoa," and even in your blog article, you talk about like the kind of, again, you get why things happened and why they did, and they work really well. But even how we map the IPv4 mapping scheme, right? And you're like, why don't we just use tuples? How come? Yeah.
Well, I mean, in a sense, tuples, like coordinate tuples, are what you have with IP addresses. IP addresses have two parts, right? They have a wide area part and a local area part, which we call the subnet piece. And you have your subnet mask, which tells you where that boundary goes between them. And that allows you to scale to a certain extent. It's a very flat scaling model, but it works pretty well, or has worked pretty well so far. And when they introduced the CIDR, classless networking, for those people who still remember A, B, and C networks from yonks ago, that was all gotten rid of, and networking was made scalable through these variable tuples or variable prefixes, essentially. But it's all like sort of steeped in the past of trying to squeeze bits into fixed size packets, headers, and based on limitations of technologies which really expired years ago. And it's, you can imagine redesigning networking today in a much more friendly and simple way.
So when I meant tuples, I was meaning more about what you were talking about in your kind of hotel room, Vegas hotel room analogy, where why wouldn't we just like building floor room, or that kind of idea?
Yeah, absolutely. I mean, I tried to make fun of the networking in that sense, even to the point of that we spend our whole time in networking today working with redundant addressing. So you've got your MAC addresses and you've got your IP addresses and LAN addresses with the prefixes. And every machine has two addresses for no good reason. Like, we don't need the MAC address if we have the IP address, and vice versa. The IP addresses are routable, the MAC addresses are not. So you may as well keep the IP addresses and forget about the MAC addresses. But all of these things are, they're subtle, they're technical, and software writers didn't really understand the implications of these when they created SDN solutions, I think. So we saw a lot of hybrid models of things clunked together to try to make something work. But actually, interestingly, just after I finished that and published that blog, I guess it was when we were doing the socket plane thing, shortly after that, along came Calico, doing layer 3 networking for containers. Quite a similar idea to the thing that I was talking about. And then much later now, you've got what's it called? Cilium, I think, is a new project. Thomas Graf and co. working on this. Very much the idea that I had in the blog, which is just putting IP addresses on all of these endpoints like you're supposed to have, because that's what the IP addresses are for.
Yeah.
Identifying endpoints, and none of this NAT nonsense. And
just get over it. Go to IPv6, right? Like, just stop this foolishness, right?
Harder, easier said than done. But
I know.
If we could get beyond that thing, then certainly.
That was. I was just going to say that one of the hacks that we thought we were going to do at Socket Plane was be sort of a hybrid. Like, do the easy stuff through kind of the classic SDN model, if there's such a phrase as classic SDN, but which would be, there were certain things that where the data plane manipulation actually kind of made sense, simpler things. But then instead of just like NSX and some of the SDN players force everybody into that kind of square peg round hole, we would go, the router pro BGP kind of the Calico stuff. So we'd be kind of Calico and NSX. And when I first met those guys from the Calico, we had just gotten sold and we were kind of redirected on what we were going to do internally in Docker. But I was telling those guys, like, we were going to compete the hell out of you because we were going to do what you do and this. But I do think I like the Calico guys. I like what they've done. which is, I remember sitting. It was like the first Docker. One of the guys gave the presentation. I apologize for not remembering his name, but I was like, no SDN. I was still drinking the Kool-Aid. I'm like, you just basically telling the world, F you on SDN. And he's like, yeah, basically, yeah. And he was right, so.
Well, I thought it's interesting to see also the story around the container networking that went into Kubernetes, where they went for a model, which I think is the right model, again, with IP addresses at the endpoints, and the indexing of those IP addresses are mapping the host name to the IP address, so you don't really care what the IP address is, because you shouldn't have to, right? Is done through the orchestrator, through the orchestration framework itself, because it has the information. And that's the obvious way to do it. You have some central, if you want to centralize anything, you want to centralize the management of the index that maps addresses to names. And by names, I mean things including services, what I guess today we'd call service discovery. But that thing that allows you to say, I need this service on the network, just give it to me. I don't care what the number is. I don't care what its MAC address is. I don't want to tunnel no ARP tables. Just give me this freaking service and we'll get along just fine. This is kind of the approach that Kubernetes is taking. I think it's the right one.
Well, does this kind of play into your, in your blog article, you do a really good analogy of the hotel, and we had some kind of good discussions about this in the soccer plane about, like, if you could do a redo, it would be kind of a namespace indexing, and of course the IP address would be all at L3. I mean, do you think that Kubernetes kind of like took the approach that you were talking about? And by the way, if you agree, then it probably makes sense for you to do a little bit of the overview of that analogy that you did.
Right. So what I said in the blog piece was that, so in networking, we have two approaches to connecting with other devices. We have the broadcast, the shout out, come in number 21, your time is up. I have no idea where you are, just raise your hand if your name is such and such. And that's noisy, and it uses up bandwidth, because when you're broadcasting like that, you're using up everyone else's bandwidth as well. So it's like having a meeting where everyone's shouting at each other around the table, instead of having the talking stick, which gets passed around and they all have their turn. But then you have your address approach, where you actually know the address you want to go to. And if those addresses are laid out according to a simple plan, like in a hotel, for instance, where you have floor numbers, room numbers by floor, and you follow the arrows and you find your way to the room directly. If there is a map which is constructed with such regularity that you know that going in this direction will get you to where you need to go, then that's a great way to shortcut all of this shouting out. So, the Ethernet or layer 2 networking is a shout out broadcast network, because it was designed for bus. It was designed as a bus technology originally. The thin Ethernet cobwebs, so I call them cobwebs. You had many devices on the same wire, but they pretty much quickly realized that didn't scale, and created hubs where you had basically one cable to each device on the end, and then they all went to a switch. So we got rid of the bus technology for everything except wireless very early on. So, the broadcasting is mostly a wireless channel thing these days. But if you're going to design networking using a routable technology like IP, then you can essentially create that. I mean, that's what routers do. They create signposts that allow you to, over a long period of time, set up these hotel room numbers, these tuple addresses, and say, I know exactly where to find this computer with this address. We don't have to do any shouting out and waving of arms to find them. So IP is kind of primitive, and we see that in the way that routing tables grow because of these signposts basically have to be learned in real time. If we had a more multidimensional kind of tuple space for networking addresses, we could scale that quite a lot better. And this, of course, is the lesson that we've learned in computing in many cases, that if you want to limit the scope of addressing or names or just identity in general, it's an identity management problem. If you're trying to limit scope, you use scope, which is namespaces. Now, namespaces in computing has a particular meaning of, we think of directories in file systems are kind of local namespaces where the name of a file in one directory, files in different directories can have the same name, but they're distinguished by the sort of sharding of the directories. In a similar way with networking, you can create namespaces, and Kubernetes has a go at doing this. I'm not sure if it's fully implemented yet, but they have this notion of namespaces per tenant. So the concept of multi-tenancy comes into the networking. And of course, Amazon Web Services have their private networks and so on. So many cloud providers or modern infrastructure providers are trying to create things like namespaces to some extent. Part of the problem is that when they do it, many of them resemble VLANs or broadcast domains rather than rooted networks. So you often have an abstraction which brings back the limitations of this kind of local area network thinking, instead of having a completely, location agnostic approach to coupling together collaborative systems. So what I did was, after writing that, and after the socket plane story, I went on to work with Cisco, actually, looking at how to scale networking for the Internet of Things, where obviously you have way more endpoints, even than, potentially even more endpoints than you have in the cloud. And they're still growing. And what you need to do then is really take this notion of scope and namespaces much more seriously, because there's no way that you can imagine shoving all of the traffic through a generic set of global addresses and names and rewriting DNS in real time to cope with the kind of dynamicism that you're going to see at the edge of the network in an Internet of Things kind of world. So you really need, because you know that you're going to have to do a lot of dynamic rewriting because you're spinning up and down containers every second instead of every 2 years. Sending an email to the DNS provider to register a new IP address ain't going to work. And we've seen, in response to that, we've seen technologies like Consul and etcd and Zookeeper, and these now faster, more localized name services, which can respond in real time to changes happening. And they're kind of designed to work well with things like Kubernetes and VMs and so on, and cloud providers and so on. So they have sort of the right idea about trying to make it more dynamic. And even in things like Consul, you see concepts somewhat like namespaces. And etcd, I think, has taken on these things as well. It's all changing so fast that it's hard to say what the current state of it is.
Consul is the HashiCorp, just in case people didn't know that, but yeah.
Right, yeah, Mitchell's HashiCorp thing. So the point is that, so what I did was I tried to take this notion of a namespace and just put it together with networking environments which had specific properties, like you mentioned, firewall rules, for instance, and try to create the notion of scope as you have in like an object-oriented system. So if you can imagine something which I called workspaces. So we have an IETF draft with my friend at Cisco on designing something called workspaces, which are essentially distributed namespaces on the network, but they don't have to be like LAN-like things. They can be distributed anywhere. But you have a sort of a security perimeter around the outside, and you have all of the rewriting of resources on the inside. So you've got your internal storage and your networking and the compute all inside the workspace. And it's a virtual boundary, and it gets allocated. And it's, I guess, Kubernetes came after this, but it's not unlike Kubernetes. If you were going to implement this, you may sort of start there with that. And it's moving very fast in that kind of direction as well. So in just this idea of separating out not just multi-tenants, but areas of interest is going to be hugely important in the Internet of Things kind of world. You're running your smart building, you are in charge of the lights, and someone else is in charge of the heating, and then someone else is in charge of the security. And these have a certain domain expertise, which means that the lighting guy isn't the security guy, isn't the heating guy, because they need to know something about their domains as well. But they also need access to control these software-defined addresses and devices and collect data and process it and feed it back and so on. So all of this new rich relationship with data being spread out to a vast number of endpoints now is not just straining the network, but it's actually straining our brains and how we can deal with information as well. So we need to wrap something around networking, not just for the sake of the routers and the switches, but for the sake of people's brains that have to manage these things.
So on the so just to take that kind of that work either you've done with the Cisco ACI stuff or the paper that you propose, and or to kind of play that out one step deeper, like you have your kind of smart building, if you will. Every device is networked, right? And so with the workspace thing, what does that look like? Does it look like some type of distributed indexing system that then interfaces with DNS and then uses like IPv6? I don't know. I mean, just for fun. Yeah.
Well, I mean, yes. I mean, yes to everything that you just said. The idea is to rewrite indirection pointers instead of rewriting infrastructure. So this idea that you actually re-provision systems and spin up and down things and reconnect things through complex protocols is kind of nuts. If you can simply change a pointer in a pointer table to redirect you to it's much, much cheaper.
Go figure.
And the ultimate expression of that is the way we do load balancing, which is equally nuts. And it comes out of the history of having to have these middle boxes, right? Where you had these basically decentralized networks and you've got traffic coming in on a single line and you're trying to split it to a bunch of servers. So you put a box in there, a physical box. But now that we do this with software, people thought, oh, let's just replace the physical box with a virtual box. And the problem, of course, with the physical box was that it was a bottleneck, as well as a single point of failure and all of those things. So now replacing it with a software one, we've not only made it equally fragile, we've probably made it less powerful than the hardware thing, slower, higher latency, and it has all the same problems as before, and you've got more of them, so it's even more of a headache. But if you could redesign your networking load balancing solution to be something that actually everybody's heard of, which an indexing system where content is rerouted to a suitable provider by contacting a directory service. This is actually how CDN works. Content delivery networks work in this way, right? You're trying to scale traffic or information. You go to a central service like DNS in that case, which sends you to the nearest server that will provide it to you. It's pre-copied, multiple copies. You get the fastest one, at a theater near you, you get the fastest one. Instead of having to go to a single point and everybody's piling onto this one giant queue like your voting thing this morning, and then having to suffer through that queue in order to then be passed off to a bunch of servers. So you can diffuse that entire centralization bottleneck by using this much more lightweight centralization of directory services, which is the approach that people are using, of course, with Zookeeper, Consul, etcd, and so on. I think the problem that's coming up there, though, is that people are using or abusing these consistency protocols, the Raft, the Paxos, and so on, again, in order to try to imagine that the systems are deterministic and make lives easier for programmers, perhaps. But I think that's probably the largest scaling problem that we have now, because consistency is simply not a scalable concept. we immediately fall back into all those cap issues.
Yeah, I mean, this is what we've talked about in the first, at least the first 3 or 4, where we talked about cap and the issues there. And I mean, in the end, these are, hard problems to solve. One, because instead of one, A, because they're hard problems to solve, but B, because we do have so much legacy. And C, we're kind of all kind of cognitively trained, in a way, which is, again, like the meta point of this podcast, which is, how, in search of certainty, which really is how do we break that kind of cognitive at every level, networking, compute, how do we do things, right? I mean, I guess the other thing I'd be interested in, well, one thing I definitely wanted to ask you, I do want to talk about the promise theory angle and all this, but there's something that you said in the article that, I thought, at least for me, I wanted to hear it explained, but you said that we should not be planning network based on purely symmetrical computational fabrics and walled gardens. Anyway, I didn't put that together. I stumped you too. There we go. All right. That's the problem of writing stuff. I do that myself too.
Completely out of context.
All right. Sorry about that. Yeah. But it was a good line, though.
I'm sure it was wonderful.
All right. Stump the Mark show.
I have to go and read that again.
No, I'm sorry. All right. Well, surely I'll ask you to kind of, play out where we've gone. Again, I know you've done a lot of work with the Cisco folk. Mike Dvorkin over there is another, the Russian evil genius who's actually a pretty awesome guy. But, but promise theories really well. Yeah.
And they actually advertise the promise theory on their website for the ACI and use many of the principles are very compatible. Mike came up with these things pretty much independently, but it fits right, it fits very much into the promise theory approach. So the ACI is an interesting kettle of fish precisely because it is much more of a distributed contract-based approach to networking.
And that's Cisco, just again, in case we're acronyming out here. Okay.
But it's also a little ahead of its time, I feel, because it brings a lot of complexity as well to the management, which we haven't really solved. And part of the, going back to this issue of the namespaces, the workspaces, trying to limit the scope of changes. I basically have a couple of rules that, if data don't need to go anywhere, don't send them over the network. Mm-hmm. But this is not the way networking people think. They want to send everything over the network as much as possible, which obviously doesn't scale. But if you could design network workspaces to contain not only traffic, but also semantics and limit functionality and purpose and tailor the functionality of a system to the specific resources that it needs to use, then you would be way much better off. And in a way, when you look at all these tools like Mesos and Kubernetes and the Docker stuff, and all of these tools that are coming up now are pieces in a puzzle that could create a future platform where this all becomes very transparent and easy. But today, all that burden is still being thrown back onto developers and DevOps people to figure it out. Well, go figure these 20 new tools or 20 new technologies and put something together on your own and figure it out. Nobody's yet created the all singing, all dancing platform to make this really easy. So I feel like even though some of the obvious mistakes of SDN in the beginning have now been rectified, at least in principle, we haven't really advanced to the point where any of this is easy yet.
No, so if you had to play, like, where do we go if make you king for a day and promise theory and networking, and we could be futuristic here, but I think you've given a great example of this kind of idea of scoping namespace, and in your article, your blog article is a great job there, and we're seeing manifestations of that and things like Kubernetes to a certain extent, Docker Swarm, Mesos, but you play the what if, given you've done a very good job of explaining to our audience what we could do in compute. What would you do?
So,
Yeah.
From the promise theory perspective, it's pretty straightforward. And promise theory isn't that hard. It's a couple of principles, and you try and apply these principles to every case. And promise theory says that an agent can only promise its own behavior, so a local behavior. It can tell you what it's going to do, but it can't promise you what you're going to do. And what that means is that the promise field, if you like, if you look at a system, the field of all the promises distributed around the system is a single valued function of its arguments. And so in a mathematical sense, it's unambiguous. It has a single answer to every question that you're trying to answer. But it still allows, even though it tries to localize as much as possible and prevent unnecessary communication, which has a nice limiting and localizing of traffic consequence, it also means that it still allows propagation between nodes that need to communicate. So it gives you a notion of scaling. So scaling is important here because it's really the scaling of agency in a system that you're trying to solve with networking. In a PC, you've got a network, which is the bus inside, that connects the processor to the memory. That's the little network. But we tend not to think about that internal network because it just works and it's there and it has, reliable properties. But it's when we go outside the boundary of a certain cell or a certain scale, like a PC, to connect one PC to another PC and create a new layer, a new kind of cellular structure, that we start to worry about the properties of the network we build at that point. Is that also going to be a bus like the old Ethernet, or are we going to create a mesh like the IP, or a switch or a hub-based network like TCP/IP? So we're still struggling with all these questions, and we're building on top of an infrastructure which is independent of the logical problems that we're trying to solve. And of course, we have this notion of control where to understand control, we usually want to centralize something about the information that we're looking at, because the thing you get from centralization is to calibrate everything on a common scale. There are not many good reasons to bring everything to a single point. It's messy, it creates bottlenecks, single point of failure, etc. But one good reason to do that is to compare things according to a single standard, which is what you do when you monitor systems and to some extent govern. So a single point of definition is good for managing systems in the sense of a policy. If you can decouple the timescales for implementation, and this is what policy tries to do, and this is what the ACI tries to do. It's what CF Engine tried to do. It's what Kubernetes is trying to do. It's trying to allow the implementation timescale to be decoupled from the management decision timescale, with a technology in between to make that transduction. And then you can do it backwards from a single point of control if you can shard a system to the point where you can always route to a single dedicated endpoint for any kind of, it's like hashing, distributed hashing. Instead of piling everything up onto a single point load balancer and trying to spread things according to some algorithm, you say, if your name is Mark, you're going to that line. If your name is John, you're going to this line. And so you immediately know, like in a hashing table, where to go. So there's no, back and forth. Anyone got spare capacity? Mm-hmm. And that, if you can make the entropy of your hashing algorithm good enough, you can spread loads in that way. The alternative, of course, is that everybody has to come to some standard agreement, which is expensive. If you're trying to get a whole bunch of hosts to agree on a consistent state of affairs, that's very expensive to do. Hence, things like consistency algorithms and cap issues and so on don't scale to very big systems. So this is another reason why we want to wrap things into scopes, workspaces which are small distributed namespaces, because they need to be small, else we will not be able to manage that consensus about what things are, what's going on in the world, So to centralize control, you basically have to incur the cost of transporting with latency all of the information So you're trying to transport as little as possible, because if you're micromanaging end nodes through the wire, as people have tried to do with netconf and old networking, SDN, OpenFlow, and so on. This is not a very scalable thing. It's a brute force thing, not scalable. And the other problem with that is that because you're going through a lot of intermediate nodes, agents in the promise theory sense, trusting messages to arrive and be interpreted correctly is a problem. Because if every time you go through an intermediate node, you lose the ability to trust or guarantee or promise what's going to happen, because an agent may only promise what it does itself, not what that thing in the middle is going to do. So, I mean, you're really, networking brings out all of these issues about trust, relationships, reliability, scalability, in a single set of issues, which we have to deal with all in one go. In the language of my book, In Search of Certainty, the dynamics of the networking, the scaling of the dynamics and the scaling of the semantics, both have to be taken into account, and both of them are complex and hard to get right. And both of them can actually benefit from this notion of workspaces or small distributed namespaces that have local resources built in.
Well, it sounds like, if I had to summarize this consistent theme that you've had all along, and the kind of workspaces idea is just, again, fits with the promise theory model, in that you kind of create atomic actors, if you will, around certain, again, you say scope, and then you allow these things to kind of, from a behavioral standpoint, adhere to that kind of promise notion, and then you don't have, in a sense, you don't worry about this trust issue, because each kind of, again, it's what you've described as promise theory and compute. Sounds like trying to solve the problem the same way in networking. I mean,
right, but there's a subtlety which I just thought about as you were saying that, which is that you may say, how is this any different from just